Hi, welcome to this video. Now in this one, I'm going to explain how the k-means clustering algorithm works without diving straight into R or Python or some other data science programming language. Now the topics we'll cover in this video are, we'll take a look at the sample data set, which we've downloaded from NOAA. It covers 25 weather stations in the US for dates between 1900 and 2021. We will also see a transact SQL query, which I'm going to use to deliberately denormalize data so that we can manipulate it using an Excel data table. We'll then see how to build a data table that extracts the data and that allows us to see what the algorithm is doing as we reassign points to a different cluster centroid and gradually reduce the sum of squared errors until the clusters are stable. We will then see how the index and match functions in Excel allow us to see which cities are assigned to which climate cluster. And then finally, we will plot the results in Excel and see if we can draw any tentative conclusions and or suggestions for further processing. It's a good idea to see the straightforward maths behind the k-means clustering algorithm. In the slide, there are 13 pseudo-random points labelled A to M. I have drawn 3 right-angled triangles from point A to 3 different centroids, the positions of which have been selected based on where some clusters of data appear to be visually at the moment. In a real project, there are algorithms that select the best initial values for these centroids, but the pseudo-random C1, C2 and C3 will suffice to illustrate the technique. 3 calculations give the distance from point A to each centroid using Pythagoras. The k-means algorithm repeats the calculation for each point and centroid. The equations are shown in the top right and the results are shown in the Excel data table bottom right, where the shortest distance from a given point to a given centroid are highlighted in green in each row. The coordinates for each point are processed by the formula in the cells A1 to B2 and labelled x1, x2, y1 and y2. From each row in this table we can select the centroid closest to each point. When that is done, a new value for the centroid's coordinates is calculated based on the means of the x and y coordinates assigned to a centroid. With the weather datasets data table, the values in the table are, in fact, the square of the distance between points and centroids. This value is called the squared error and is the figure used to help select the closest centroid. With new values for the centroid's coordinates, the whole calculation is repeated to see if any points assigned to one centroid are moved. When no more points move to a different centroid, the process is finished, and the results can then be used to plot a chart of some sort to visualize what is happening. So on the screen we can see inside my SQL Server Management Studio, not to worry about that, and inside the database I've got the NOAA data here. On the screen you can see that I've issued a simple command here. I've asked it to select all, that's what the asterisk means, from the database table, and I've restricted my output to where the city is equal to New York. So that gets output to the actual screen here, and you can see the different fields: station, observation date, location, city, type of climate, Tmax for maximum temperature, Tmin, Tmiddle, and I want that I added, which isn't in the NOAA data, and that is the height above sea level for the actual station. I did that because I had some ideas about whether the altitude would be involved. More data science thoughts. I can change the name of the city here simply enough. I'm going to choose Chicago because I know it's in there. And if I run that, execute that query, I get a different set of data. I also find that I got 27,442 rows down here for Chicago compared to a larger number than that in New York. If I run that again for New York, you can see that New York's got 40,600 rows. So that's the data. Now what did I do with it? I actually pre-prepared the data a little bit. This is a slightly more complex query, don't worry about it, but all it does, you'll see in a minute, is to actually take some of the data and combine it together. So I'm just going to run this particular query. It's going to select the station, the city, the height above sea level. Then it's going to do 3 calculations where I'm asking it to calculate the average max temperature over all the records, something that I've called the temperature ratio, and also I've included here a ratio of max temperature to the ratio. I'm taking it from the table, I'm grouping it according to station, city, and height above sea level, and I'm ordering it by the 3rd column, whatever comes out. That produces for me 25 rows, right? 1 row for each city where records have been kept. And here you can see we've got Denver, height above sea level 1600, the mean max temperature 64.7. These are all in Fahrenheit, these temperatures. The temperature ratio, and then at the end something which is me taking 2 columns and sticking it together. That's to allow me to put the data into the Excel data table. You see that happening a little bit later on. That's a bit naughty in the world of databases. You shouldn't go denormalizing your data, by which I mean taking data from 2 separate rows and joining them together. One last thing before we leave this section, I'm just going to bring up this bit here. I'm going to find out how many records there are altogether in the database, select the count, call it N records, that's what that text means, from the database. And there you go, 723,398. So all these calculations are happening over a lot of data. Although I do know that round about 15,500 of them, the records are nulls. They haven't got any data in. So there are some imperfections. Right, let's move on then to analyze the data. So here we can see the data table. In the column there, that is the information that we output from the SQL server. It combines together the maximum temperature and the temperature ratio. Across the top, some centroids that I pseudo-randomly assign some coordinates to. And in the middle, the system is calculating for each combination of station and centroid the squared error. In each case, there's one of those which has got the lowest squared error, and that is the centroid to which we will assign each station. So this station here is assigned to this one, which is that centroid there. Now to find out which centroid goes in this column down here, I've used the index match function combination, which I describe in a separate video. So if you're not quite sure what's happening there, you can go and watch that video and come back, or you can watch the rest of this and then go and check the index match function later on. So all that's happening here is that the coordinates for each point are being extracted by using some text functions here. So in this case, the left function is going to take the left 2 most characters from wherever it's picking them out. In this case, it's picking them out from up here. Okay, the AF2. And in AF2, it's going to pick out the leftmost characters, and the number of characters I want will be those characters in front of this semicolon you can see in the middle of this formula here. And then I subtract 1 from that because the semicolon is in position 3, therefore I only want the 2 characters in front of that. When it comes to the y coordinate, the function reads from the right, and this time it's the same sort of thing. We're going to read the right from this particular thing here, and we're going to take the length of the whole string minus the position of the colon, and that will tell us which characters to extract. Once we've got these characters, we can just ask this formula to apply Pythagoras, well, Pythagoras without the square root sign to give us the squared error. And in each case, I have very carefully made sure I'm working with data, because the text functions produce text as output. So here I'm making sure that any text that looks like a number, which Excel should process anyway, is actually recognized as a number by explicitly using the value function around the output. So that's how that particular bit works. And what we've got at the bottom here is a sum of the squared errors. To find the sum of the squared errors, I'm using the sum if function. In this particular case, that sum if function, when we open it up, it uses the AI4 to AI28, which is this piece running down there. It looks for whatever A3 is, which is this cell right at the top here. And when it finds a match in this range for what's at the top there, it looks back across into the adding up range, which in this case I've made AE4 to AE28. And if there's a match between the number on top and the number going down the side, it will add up all the way down those particular values. And that's how we find the squared error for each individual centroid. Here, the squared error says 236 in total. What we do now, as we have been able to assign each station to one of these centroids, 4 different centroids, we recalculate the position of the centroid, take its X and Y coordinates for each point in that centroid, assign to that centroid, and produce some new centroids. And we'll see that in the next section of the video. So here's the next part of the data table. All we've done here is updated the coordinates for the centroids across the top here, and just asked the data table to recalculate everything. What we notice is at this point here, 78.9130, which was assigned to the centroid 75.1.4, is now assigned to the centroid 82.6.1.35. So that single change will cause an update in the assignments, an update in the squared errors, and we therefore need to just redo that until no more stations are assigned to no more new centroids. At that point, our algorithm is finished, and we can then analyze the data using perhaps some kind of graphic to establish if there are any patterns that we can see in the data. So that's the end of that little section. So now we've arrived at the final part of the video, and what you can see on the screen here is I've taken the results that we processed using the k-means clustering, and I've put them into a table here in Excel, and I've arranged them in order of the cluster to which they have been assigned. Then I've just asked Excel to show me a scatter plot of the data, chosen one of the standard possible formats for your charts, and you can see that in front of you. I've tried to keep the color scheme the same. And I think you can see that we've done quite well here. We've got a group in teal, I think that color is. Cluster 1, where we've got San Antonio, Houston, Dallas, Miami. All of those are down in the southeast corner of America. Phoenix is up Arizona way, and Riverside has been assigned here as well, but I haven't actually put it into the circle. What Riverside and Phoenix share is that they're actually quite high up in the sky. They're about 200 meters up. The next cluster along here, you can see Atlanta, Charlotte, San Diego, Los Angeles, different sides of the country, but with similar patterns of maximum temperature versus the temperature ratio, the ratio between the lowest and the highest. Across here, you can see another group. They're slightly higher. The centroid is slightly higher. Baltimore, St. Louis, Philadelphia, New York, Portland, all together in that group there. oval for, as Excel calls it. Right at the top, Denver's in the same group, but again, Denver is high in the sky. It's over 1,000 meters up. And the last group here, the last cluster, Minneapolis, Detroit, Chicago, Boston and Seattle. So we can learn something from that. We can see there are some sort of climate areas there based on the max temp versus temp ratio. And it's certainly the whole point of data science, not the programming, not the R, not the Python, but the aim of the data science is to see what you can see and how might that impact the real world. And I think there's some fairly clear things you could investigate further in those charts. So I hope you found that introduction to k-means clustering useful to show where we can come from raw data through a process to deliver some kind of workable data and information that people can then use to study things in more depth or to come to some sort of conclusion. So I'm going to end the video there. Thank you for watching, and I'll see you in the next video.